Okay, so let's talk about Anova. This is one-way analysis of variance. And we're going to use one-way ANOVA when we want to compare the population means across more than two populations. When we only had two populations, we could use a z-test or a t-test. Okay, so this would come in if you want to compare the mean mileage of, say, 4 brands of tires, so then you'd have 4 groups. Or you want to compare the mean weight loss of 5 different diets, then we'd have 5 groups. And so we just take a sample from each of the population and we want to compare their sample means to try and decide if we think that their population means are equal. So again, just like we did when we had two populations and we did a two-sample t-test or z-test. And so our null hypothesis is going to be that mu1 equals mu2 equals up to mu(I). So the population means are all equal. So if I have 5 different diets, then I do mu1 equals mu2 equals mu3 equals mu4 equals mu5. Okay. Then the alternative hypothesis, now pay very careful attention to this, the alternative hypothesis is that at least one population mean is not equal to the others, or that not all of the mu(I)s are equal. Okay, this doesn't tell me which population mean is different. It doesn't tell me that it's necessarily 1, it could be 1, it could be 2, it could be 3, it could be all of them are different. All it says is just at least one is different, and that's the only conclusion you can draw from this test. You can't tell me which one is big, you can't tell me which one is small. All you know is that at least one population mean is different. Okay, now think back, and we learned that if we have a population, we're drawing a sample, so let's say the population is all the people in Utah, and I'm interested in their heights. If I pick 10 people here, I'd get a sample mean height. If I pick a different 10 people, then their sample mean height would be different, and another 10 people would give me yet again a different sample mean height. And so that just means we have variability in our samples. So even if our population means were equal, so all of the diets really cause the same mean weight loss, you'd expect some variability just based on which people you pick, so your sample means could vary a little bit. Okay, and so what we want to know is, are these differences in the sample means, is that due to chance or our sampling variability, or are the differences actually statistically significant? So one of the things we want to do is compare the variation between the groups, so between the sample means. So if I say between the groups, I mean how are the sample means different? So here's our box plots. The sample mean is the line in the middle, so sample mean 1, sample mean 2, sample mean 3. Notice that my sample means are different, but I also have variability within the group. So within the group, notice I have observations that are here, I have observations that are here. So there's quite a bit of variability within the group. Okay, and so because there's so much variability within the group, the sample means that I observe could be different just due to chance or sampling variability. And there's probably not a difference in my population means in this example here. Now if we come over to B, notice it's still about the same difference in my sample means, but within the group there's hardly any variability. Okay, and so this makes me think that there's hardly any variability in the group. This probably really is my group mean, and this probably is my population mean, and probably close to this. And so there probably actually is a difference in our population means. And so these differences in the sample means are likely to be statistically significant. Okay, so again, we want to compare the variation of the sample means between the groups and the variation within the groups, and just see which variation is bigger, and that will tell us whether our population means are actually different. Okay, so if the variation of the sample means between the groups is bigger than the variation within the groups, then that's the sign that our population means are different. Now we have 3 sources of variation to consider in the data. So your groups, or some books call it treatments, is the variation between the group means. So from here to here to here. Now the error, or some books or tables call it residuals, is the variation within the group. So how much variation do I have within a group? So variation in group 1, variation in group 2, variation in group 3. And then total is just the total variation in the data. So here you have everyone in the population, or all 3 populations. They all have, say, different weight losses. So you might have someone loses 1 pound, someone loses 100 pounds, and this is your different variation. So just all the total variation. Then some terms that come up in the lesson is sum of squares. So sum of squares is the sum of the square deviation. So this is how much the data deviates from the predicted values or means. So SST is the sum squares total, so the variation of the data around the overall mean. So if you put all the data in one group, you just get one big mean. So how much does the data vary around the mean? SSG, variation of the group means around the overall mean, and SSE, variation of each observation around its group mean. Okay, so actually there's a better picture if I come way down here. So here's an example we came to later. Notice there's 3 groups, and this program actually puts a line at the overall group mean. And then this little bar is each of the group means. So the SST, the total sum squares, is take each value and see how far it is from the overall group mean. Okay, so you do each value from the overall group mean. SSG, sum squares for the group, is take each group's mean and compare it to the overall mean. So from the blue line to the dotted line. And then finally you have SSE, so within the group error, so you take each value and compare it to its group's blue line or sample mean. Okay, so those are our three sum of squares. Then you also have degrees of freedom for each one, because we're used to using degrees of freedom now for our t-distributions and our chi-square. Okay, so your sum squares total has degrees of freedom n-1. Your sum of squares for your group has degrees of freedom I-1. I is the number of groups, n is the total sample size. And your sum squared error has degrees of freedom n-I. Now, interestingly enough, your sum squares total equals sum squares groups plus sum squares error, and degrees of freedom total equals degrees of freedom for the group plus degrees of freedom for the error. Okay, you also have mean squared error. This is something that comes up in a lot of terms in a lot of different statistical tests. But mean square is a kind of average squared deviation, and what you do is you just take the sum of squares and divide by degrees of freedom. So if you want the mean squared total, then you just do sum of squares total divided by degrees of freedom for the total. Okay, MSG equals SSG over DFG, and MSE equals SSE over degrees of freedom for the error. Okay, so it makes it easy to find. Okay, then you actually have the Ftest. So again, remember, I is the number of groups, n is the total sample size. Oh, I forgot to say, I'm making this movie for sets 2000 and 3000, so if this notation looks a bit different, it's because it comes from the 2000 book, but the concepts are the same. Okay, so you have an F distribution. It's not symmetric. Okay, and it actually has two different degrees of freedom, which we call the numerator and denominator degrees of freedom. Okay, so your F statistic is MSG over MSE. So remember, MSG is kind of your deviation between the groups, the variation between the groups, and this is the variation within the group. So if you think about it, if you have population means they're actually different, you should have a lot of variation between the groups. And so this number would be bigger than the bottom number, and so you'd have a big overall statistic. Okay, so when the alternative is true and your population means are actually different, then the F statistic will be large because you'll have a lot of variability between the groups. Okay, so when you get a large F statistic, you reject the null hypothesis. Okay, the p-value will be the area to the right of your F statistic. Okay, this is what a typical Anova table looks like. They'll change the order of the columns, or they might name these treatment or residuals, but all of the same information is there. So you have degrees of freedom for the group, error in total, you have sum of squares, you have the mean squares, and it will tell you the F statistic. You also have the coefficient of determination. So R squared is actually SSG over SST, and R squared tells you the percentage of variation that's explained by the differences in the group means. So if R squared equals 0.11, then you can say 11% of the variation is explained by the group means, so the actual groups have different means. And the rest of the variation would just be the variation that comes within a group. Okay, so here's an example. We have number of friends and social attractiveness. So a sample of 134 students was taken. They were broken into groups based on how many friends they have, and then they're each given a social attractiveness score. And we want to know, is there a difference in the population mean social attractiveness score based on how many Facebook friends the group has? Okay, so notice they're broken out into these 5 groups. Okay, so our null hypothesis is that mu1 equals mu2 up to mu equals mu5. So all the groups have the same mean social attractiveness score. And the alternative hypothesis is that at least one population mean is different. That doesn't tell me if it's the first group or the 5th group or groups 3 through 5. It just says at least one population mean is different. You know, this output tells me the number of sample, or the people in each sample, the sample mean, and the sample standard deviation for each of those 5 groups. You can look, if you want, at histograms and kind of see that each group is kind of normal, maybe not too close, but kind of. You can see there's a little bit of variability. So this group looks lower than this group looks. You can actually, at least for me, I can see it a lot better in the box plots. So notice these 4 box plots all seem to have pretty close to the same sample mean. I would think that they probably wouldn't be statistically significant. However, this group looks like it might be a little bit lower, but let's look at the actual test. Okay, so I used Megastat to get this output. You notice again, just here's their overall conclusions. So For each group, it tells the sample size, the sample standard deviation, the sample mean, and then you have the overall sample mean, overall sample size, and overall sample standard deviation for if you put all the data together. Okay, coming down, so they use treatment instead of group, but it means the same thing. You have your sum squares for your treatment, sum squares for your errors, sum squares total, degrees of freedom for each one, your mean squared for each one, your F statistic, and your p-value, which is really all that you need. Okay, so your p-value, because that's a small p-value, we reject the null hypothesis, so we conclude that at least one population mean is different. Again, that doesn't tell us which one. There's actually, you do what's called ad hoc analysis, and you'd go back and you do some different tests once you know that at least one is different, but we don't learn about those in this class. So all we know is at least one group has a different mean social attractiveness score than the other groups. Okay, as far as what you have to do for your homework, all you have to do is be able to look at the table and read me information. If I ask you what's the degrees of freedom for the treatment, tell me 4. If I ask you what's the F value is, tell me 4.14. Most of all, given the p-value, be able to give me this information. And that's it. Okay. So example 2, we compared the lengths of flowers in millimeters for 3 species, and we want to know are their mean lengths the same for each of the species. So again, the null hypothesis is that all these 3 species have the same mean length, and the alternative is that at least one species has a different mean length than the other species. Okay, so this is the output. Again, we have 3 groups, so I would be 3. For each group, it tells you the sample size, the sample mean, sample standard deviation, and then it tells you overall, so this is my overall mean, overall sample size, and overall standard deviation. Notice that's a lot of standard deviation compared to the standard deviations within each group. Okay, so come down here, notice your sum squares between the groups. Notice how big that is compared to the sum squares within the groups. Okay, that tells us that our population means probably are different because we have a lot of variation between the groups. Degrees of freedom, F statistic, that's a huge F statistic, and my p-value is 1.92 times 10 to the negative 27. That's just virtually 0. Okay, so that's a very, very small p-value, which means we'll reject the null hypothesis, so we have very strong evidence that at least one of the species has a different mean length than the other species. And just to look at the box plot again, so notice this is my overall group mean, or overall mean for all of the data if you put it together. And look at the difference between my sample means. That's a huge difference in the sample means compared to how much difference there actually is within the group. There's almost no variation within these flowers of the same species versus how much variation there is within the sample means. And so we think that there is a difference in our population means.